All right, here's part 2 of a video for the second example in class 14. Rigid body, kinematics, velocity. In the first part, we did this same problem using traditional vector math. And now we're going to use the 3-diagram method to find the velocity at c. So, in similar issue that we have when we're doing with vector math, we don't necessarily know when we're starting out how we're going to find that velocity of c. We have to look for evidence on things that we do know to try to get to that final destination. And what we would come across eventually, if we got stuck, if we just went head straight forward and tried to get the velocity of c directly, we would quickly find that we needed to know what the angular velocity of the piece was. And that when we could find that we're able to find that velocity, angular velocity, by analyzing points A and B first. So we'll draw this piece here, and it doesn't like my palm resting on the thing, and I don't like what those look like right here. So let me try to draw this. I wish there was a little more resistance to the pen. It makes it difficult to make this nice and neat. I'll just be a little bit more careful. That's what I'll do. Just go a little slower. Right there. And hopefully I made those big enough. Those are our three diagrams right here, and I'll go ahead and draw the little points onto there. And let me draw in the things that I know, and maybe I'll put in like a little color right here. So I know the velocity of c right here, velocity of c. Because I know the velocity of c, that's going to be the thing that I'm going to use as my reference. So I'm going to place the velocity of c at velocity of at a, and then I'm going to pin it at c, like this right here. And now it's going to spin about that point and in order to get the relative velocity. And we know that that's going to end up being along a line that's perpendicular to that relative velocity of A with respect to C is going to be perpendicular to that position. Right here, to their along there. So it's going to end up on that line. Now the question, this often comes up, we might recognize already that it's going to be clockwise, but quite often there might be other scenarios where this big idea is going to be the key to try to reason out or to think through why something is moving in the way it is. Or if we end up finding that we made a wrong assumption, and like we choose something negative and we get a negative answer, and we're like now we're like confused. Is like, which direction is something actually rotating? We can reason through it with the following logic. So try to follow along, if you will. We take a look at these 3 diagrams, and we're really looking up at that spot. We're really focusing in on that spot. That's the purpose of these 3 diagrams. And we know that the velocity of A has to be along this line. So I've drawn in, like with this little red little dashed line right there, that it's got to be in that sense. And maybe we'll just play stupid. We don't know if it's to the left or to the right, but we can kind of guess from this particular problem it's going to go to the right. But we know that there's no vertical component to that. So from the equation that we'll write out, vector equation that's associated with this right here, the velocity of A is equal to the velocity of C plus the velocity of A with respect to C. If we broke that down into x and y component, right, we would know that there is no y component to A. It's completely devoid, but it starts out with a y component at C. So what can I possibly do over here in this relative one that's able to get rid of all of the vertical component? Well, the only way that's possible is if that velocity, that relative velocity of A with respect to C is going upwards in that direction, which means this has to be in the clockwise direction. Okay, here is, back a video up, or I'll try to re-explain. This is one of the most critical things, and one of the reasons why we're using this 3-diagram method, because we actually gain insight into why things happen. All right, not just going through the vector math, but actually understanding what's actually taking place. And so in order, once again, I'll say it again, in the x direction of a 4-point A, it's going to have only x direction velocity. In the y direction, there is no y direction component. But based on this equation, as we've written it, that means that something has to happen over here in this relative velocity to get rid of the vertical component, so that, and when the result will be that A has no vertical component. And the only way that can be true is if this relative velocity is one that's created from a clockwise motion. All right, so in terms of just solving for the thing that we want to solve, we go into the y direction right here. And this could be, okay, so this is a very useful method, but it does have like a little flaw to it. We need to be able to break things into components right here when working onto something. So we need to carefully draw our diagrams and look for angles. So that angle right here is theta, that's given. So the angle up here has to be theta as well. That's a little minor difficulty that could be a little annoying. You have to be careful and be very careful when drawing the piece. In fact, it might be better to use a ruler. But when I use a ruler on the surface, it gives me all kinds of wacky things taking place. So I would have made a much better, neater diagram to be a better example to you on what to do. But making that diagram carefully, and especially the angle. Sometimes you need to exaggerate the smallness of the angle, because if you use a 45, if it's drawn at 45 degrees or looks like it's 45 degrees, a lot of times you can't decide which one is the same angle right here between this known one, and whether it's this one or it's the complementary angle to it. But right here, we've drawn it well enough so we could see. So in the y direction, we break down from the diagram, right? So the diagram is the one we focus on. In the y direction, we know it's 0 here at point A is going to be equal to negative, and we were given that it's downwards at 1.5 right here. And then we see in the y direction, right, up here, I'll kind of circle it up there, that has a y component of that. And this is an important thing people will often mess up. What we're writing here is the components, right, of the parts, the pieces, right? So it's going to be and we can go ahead and, without writing extra steps, say that we know that omega ABC, that the magnitude of that relative velocity is omega ABC times that length AB, right there. So but it's only the vertical part of it right here. So we go plus omega ABC times, and this is going to be 4. We have that up there. 4, and it's going to be times the cosine, right? So it's only the vertical portion, which happens to be this adjacent side right there, the cosine of our 25 degrees. And from that, we're able to find omega ABC is going to be 0.4138 radians per second, which is, of course, the same thing that we got in the other method. And from our diagram, we established that that was going to make it clockwise direction. And if we wanted to be thorough, we get the x direction onto this right here. And we know that it's VA completely, and that there's no right here, and there's 0 for right in there. And here it's going to be also going to be a positive direction, so it's going to be plus 0.413 8. Why'd you leave the 8 out? And times our 4 and times our sine right there, because the x component is opposite from that angle of 25. And of course we get the same thing as we got in the other problem, 0.6995 feet per second. But we didn't really need that part of it. So now what we do, because the problem is actually to find the velocity at c, what we want to do is to draw a new diagram, new set of diagrams. We could reuse this diagram up above. Oh, by the way, I think I just messed things up all over the place, didn't I? You guys would have caught me in class on this. So let me try to salvage this. I don't have the time to really re-record this, but let me come up here. That should have been B here. Should have been B right there. B. I should have put B everywhere. I apologize for that. All of these should have been B's. Should have been a B. Yeah, okay. I don't know what I was thinking. That probably distracted you, those of you actually paying attention. So I'm sorry that I made that. Hopefully you'll forgive me. So we want to redraw all of this, these diagrams. But this time we're going to use point C. And I would definitely advise that you use a lot of space. Don't try to economize the page. It just causes problems. So in this diagram right here, we know that the velocity of B is downwards right here. And we're going to use that as the reference. And so that's the velocity of B, and we're going to pin it at B. And we know that the rotation is clockwise. Our goal, though, on this diagram is to find the velocity at C. I'm going to draw that as components, velocity of C in the y direction, and I'm drawing them as positive. Velocity of C in the x direction, even though truth is I know what direction it's going to be, but let's just pretend. So we're using the velocity B right here, and for this guy right here, we know already what direction it's going. So we take the velocity, and this is going to be the velocity of C with respect to B right here, which we happen to know is omega ABC times L. I believe this is BC. Did I get that wrong on the other page too? No, I got that right. It was LAB. I just kept calling it C all the time instead of B. But we know that's going to be true, that's the magnitude of this. And oh, by the way, important maybe to check out as we're doing this, the angle onto the thing is right here, right? So let's draw it over there. That theta is right there with respect to vertical. So writing out the main equation, velocity of C is equal to the velocity of B plus the velocity of C with respect to B right here. We could go in the x direction right here, and we write VCX is equal to, well, focusing on this point, remember this is the point of the thing that we're looking at. It's going to be 0 here in the translation part of it, and then looking over here, we'll see that, well, it's going to be in the negative x direction, so it's going to be minus our omega ABC, which we found to be 0.4138, and that length right there was 6, but it's only going to be the sine of the angle of the thing, 25 degrees component of it, and we find that it ends up being negative 1.049 feet per second, which is of course what we got in the vector math part. Doing the similar thing here in the y direction, we know that we have, this is completely in the y direction, the velocity of b is entirely, so it's 1.5, and then we also have negative, right here, we see that this is completely in the negative vertical direction, so 0.4138 times 6 times the cosine, because it's the adjacent to get the vertical up there, 25, and so the answer is a negative 3.750 feet per second. And that's of course what we got in the other method, and we could write the thing out again, either way that we wanted to. Let me hold off on writing that, and let me just finish up with the vector math, the vector triangle method here. All right, so it's really good in the vector triangle method to also use the 3 diagrams. So I'm going to repeat that up here onto this, and I think I'm out of new colors as part of this. I guess I'll go purple onto that. And this equation right up here could be represented by looking at this point right here. So if we want the velocity of A, what we want to do is add to it the velocity of B, add velocity of B, which is a vector right there, downwards, and we're going to add a vector right here that we know the sense of it, right, has to be up along this length right here. And what vector can we add to that will make A completely horizontal? It has to be in this direction, velocity of B with respect to A, right there. And then if we add A plus, velocity of B plus that velocity of B with respect to A, we go, of course this goes nose to tail, right there when we're adding them, and then the solution right here is tail, nose right here. And that's not incredibly difficult to put together right there. We know what we could use. By looking at this carefully right here, we could figure out that right there is going to be the angle right there. So like looking up at our diagram, we could see that this theta is going to be right in there. So, and because this is a right triangle, it's relatively easy to figure out the velocity of, did I write this wrong here? Somewhere I did. I think it was supposed to be velocity of, yeah, I think I wrote this wrong. Sorry. A with respect to B. Yep. We can find the velocity of A with respect to B by taking the velocity of B and dividing it by the cosine of theta. Right there. That makes sense, right? And so you get 1.5 divided by the cosine of 25, and you end up with 1.655 feet per second. But we know from up here that the magnitude is just going to be so the omega ABC is going to be the velocity of A with respect to B divided by LAB, and what we're left with is we're fine 0.41. Excuse me, I should write out the numbers. 1.655 divided by 4, and we end up with the 0.4138 radians per second, which is what we knew we would get. And we could also find the magnitude of VA by doing a similar thing with the sine of theta, or we could actually use the tangent, whatever. we're able to find this. Now, that's the velocity triangle for that part of it. The velocity triangle for here is a little bit more complicated. Once again, we're reusing this diagram up above. We find the velocity of c, knowing the velocity of b right here, and we can get that and we do know what the velocity of c with respect to b is going to be. Yeah, so we could find the velocity of c with respect to b is just going to be omega abc times lbc. That's going to be our 0.4138. Where'd you go? Yeah, 41138 times 6. So we end up getting that it's going to be, where'd you go? 2.483. Is that true? Yes. Yeah, and that's going to be feet per second right there. So this is the velocity of b. We're down. We're going to add to that this vector up here. So it's going to be down that way. Velocity of c with respect to b is this magnitude, and we're going to have to make a little bit of room here because there's some angles that we need to see with respect to b right here. And we do know, if we drew a line straight down right here, that right there is going to be theta right there, right? Because we have that theta. That's the angle that we want inside there. Okay, so let me complete this. All right, so we're writing out this equation right here with our triangle, and we'll find that right there is going to be the velocity of c. Now we have a whole bunch of issues in trying to find these magnitudes based on this. We know the magnitude here of b, and we know the magnitude of vc with respect to b. If we want to get some angles, we can find, we do know, based on what we've seen right here, we could find this angle. I call it beta, right? Because we know that beta is going to be 180 degrees minus 25, so it's 155. So with this triangle, we have two sides and an interior angle between there. And that is the law of cosines that we can apply. So using the law of cosines, we could look at this thing and break it down. And I won't go the c squared equals a, remember the law of cosines is like c squared is equal to a squared plus b squared minus 2ab cosine, and we'll go capital C, meaning that capital C is the angle that's opposite of that little c right here. So along those same lines, we could find what the velocity of, or the magnitude of the velocity of c that we're looking at right here by taking the square root of the velocity of b squared, that's one of the sides, plus the velocity of c with respect to b squared, that's the other side, minus 2 times that, I don't need to put in parentheses, VB times VC with respect to B times the cosine of beta. And if we do all of that wonderful stuff right there, we're able to find 1.5 squared plus our 2.483 squared plus our 1.5, 2.483 cosine of our 155 degrees, we end up finding it's 3.894 feet per second, which is the same thing that we got using this other method in the previous video right there. So isn't that exciting? Yay. And now if we want to actually get the direction of this, because it is a vector, we need to find this angle up here. Yes. But now that we have 3 sides and an angle, we could use the law of sines, right? And we can go the opposite one. So I decided, I think, to go, I can't even remember what that's is that a psi, a PSI thing? I think that's what that's called. Or maybe it's a phi. I think it's a phi. Anyway, we could find the VCB divided by the sine of that is going to be equal to VC, which we just found, divided by the sine of beta. And then we're able to find what that angle is right there. But of course, we prefer not to use a quadrant that is based off of the vertical. We'd rather have a quadrant based on the horizontal. But so what we would end up finding, if we applied this, with that this was like 15.63 degrees, but we would need to subtract it from 90, and we would end up finding it was 74.4 degrees right there, which is, again, the same answer that we got up over here. All right, so these are really, really long and worked out. The benefits, I think, it's this is the best way to go, is to use this method with the three diagrams, because it combines everything together and you get to see. And then to also be able to check with a rough, not necessarily rough, but a careful sketch to see what the legs are and the dimensions of this triangle can help to confirm. And it's especially useful when you don't get an expected result. And boy, is that true in lots of dynamics problems, that you get a result that isn't what you expected, and you have to try to make sense of it. So using these tools, you can pick it apart. So that's the end of the show here. I'll make some more videos, but hope everybody's doing pretty well. And it was a 26 minute. That was a long one.